everybody, this is the lecture on section 6.3, Taylor series and Maclaurin series. So what we want to do is the following. We want to suppose that f of x is a function with infinitely many derivatives at x equal to a. What does that mean? That is, f(0)x equal to f of x exists. F, and look at the notation here, this is a little new, exists at x equal to a, at x equal to a. So the zeroth derivative of f of x, which is just f of x, exists at x equal to a. The first derivative of f of x, which is f prime of x in the more usual notation, exists at x equal to a. f(2)x, which is f double prime, the second derivative, exists at x equal to a. Third derivative, 1, 2, 3, exists at x equal to a, right? So on and so forth. Fourth derivative, but I mean, of course, we don't keep doing these little hash marks up here. Exists at x equal to a, all of them, right? Fifth derivative, sixth derivative, seventh derivative, they all exist, okay? So suppose that's the case. Now, suppose that f of x has a power series representation. an x to the n has a power series representation. And this, let's write out the terms, that's a0 plus a1x plus a2x squared, a3x to the third, a4x to the fourth, a5x to the fifth, so on and so forth. Plugging in x equal to 0, right, all of this is 0 except for a0. Right, a0 is f of 0. Now, let's take the derivative of this. F prime of x is equal to, well, that's 0, that's a1. a1 plus 2a2x plus 3a3x squared, 4a4x to the third, 5a5x to the fourth, so on and so forth. Plugging in x equal to 0, we have f prime of 0 is equal to a1. Let's do it again. Take second derivative. Well, that's 2a2 plus 3 times 2 a3x plus 4 times 3 a4x squared plus 5 times 4 a5x to the third, so on and so forth. Plugging in x equal to 0, I have f double prime of 0 is 2a. These are all 0. 2a2, sorry. So, right, a2 is equal to f2 of 0 over 2. Well, 2 is the same as 2 factorial. Same thing here. a1 is equal to the first derivative of f at 0 over 1 factorial, which is just 1. Sorry, let me rewrite that. First derivative at 0 over 1 factorial, which is just 1. Here, a0 is equal to the 0 derivative over 0 factorial, which is again 1. 0 factorial is 1, it's not 0. Let's take the derivative again. The third derivative is equal to, well, that's 0, and this one you just get 3 times 2, a3, plus 4 times 3 times 2, a4x, plus 5 times 4 times 3, a5x squared, so on and so forth. So, f triple prime at 0, this is 6a3, well, 3 times 2, a3, and these are all 0. So, a3 is equal to the third derivative at 0 over 3 times 2, but that's 3 factorial, etc., etc., etc. So we call if, and this is a big if, f of x is equal to the sum n equals 0 to infinity a n x to the n, then a n, well, fx is equal to the sum n equals 0 to infinity nth derivative of f at 0 over n factorial x to the n. So if f of x is a power series representation, this is it. Okay? This thing here, this is called the Maclaurin series, or the Taylor series centered at 0 for f of x. Nth derivative at 0 over n factorial x to the n, the Maclaurin series, or the Taylor series centered at 0 for f of x. So this is either called the Maclaurin series or the Taylor series centered at 0, or just the Taylor series. So if f of x has a power series representation, then that's it. It looks like that. These are those coefficients. Similarly, if you don't want to center it at 0, you can center it at a, in which case it looks like this. Is the Taylor series centered at x equal to a for f of x. So we have the Taylor series centered at 0 and the Taylor series centered at a. You can do it either or. Okay, usually 0 is an easier one to deal with, but for that case, in that case, this is what it is. Oh, I'm sorry, I shouldn't do this yet. So the question is, does the function equal its Taylor series? Okay, so when the Taylor series exists, for f of x exists, is f of x equal to? And the answer to this is pretty much yes. So we'll get to that in a moment. But before that, let's do some examples. Let's calculate some Taylor series. Okay. So we'll see that the answer is yes. Usually. Especially for these really nice functions that we like to deal with. So, for example, calculate the Maclaurin series for cosine of x. Okay, so we've got f of x. So we have to know all these derivatives. Okay, but it's not hard with cosine of x. All right, f of x is cosine of x. First derivative of f of x is minus sine x. Second derivative is minus cosine. Third derivative is sine. And then the fourth derivative is equal to cosine again. Right, so it goes in periods of 4 different derivatives, right? 0, 1, 2, 3, 4. And then 0 and 4 are the same. So these are the derivatives for cosine as you keep taking successive derivatives. Now the center of the Maclaurin series is at 0. So we need to know what that is. f0 of 0, cosine of 0 is 1. f1 of 0 is sine of 0, which is 0. Second derivative at 0 is minus cosine, it's minus 1. Third derivative at 0 is sine of 0, which is 0. And then the fourth derivative at 0 is 1. And so on and so forth like that. So it's, fourth, fifth, sixth, seventh. All right, so 1, 0, negative 1, 0, 1, 0, negative 1, 0, so on and so forth like that. So the Taylor series or Maclaurin series for cosine of x is, it's the sum n equals 0 to infinity, fn of 0 over n factorial x to the n, right, where the terms for n odd are 0. So it's just the even ones, right? Just the even ones. So sum n equals 0 to infinity, starting with plus 1, minus 1 to the n, minus 1 to the n over 2n factorial. Don't forget that factorial, right? So we're going just in the even order terms. So for the 0 term, it's 0 factorial. For the n equal to 1 term, it's 2 factorial, right? 0 factorial, 2 factorial, 4 factorial, 6 factorial, 8 factorial, so on and so forth. So it starts with plus 1 over 0 factorial, minus 1 over 2 factorial, plus 1 over 4 factorial, minus 1 over 6 factorial. So it looks like that. X to the 2n. All right, later we will see that cosine x is equal to the sum n equals 0 to infinity. It's Taylor-Maclaurin series, minus 1 to the n over 2n factorial x to the 2n, and then get this for all x. So the interval of convergence is infinite. Cosine x is always equal to its Taylor series for every x. Similar examples. Cosine x, or we did cosine. Sine of x is the sum n equals 0 to infinity minus 1 to the n over 2n plus 1. So here it's the odd terms that are non-zero. So this is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, so on and so forth like that. E to the x is the sum n equals 0 to infinity 1 over n factorial, just positive 1, x to the n. This is for all x. This is for all x. E to the sine x, cosine x, e to the x. Other, excuse me, other examples, here we are. Standard examples that you need to remember are given in, well, there should be a table of these things. Although I'm not seeing one. Oh, come on. They don't have them in there? Maybe at the beginning of 6.4. Yeah, here it is. So, the Maclaurin series for e to the x, x to the n over n factorial. Sine x, cosine x, natural log 1 plus x, arctangent of x. We did this one already, because that comes from the geometric series. 1 plus x to the r, right, is this. And we'll talk a little bit more about this in the next section. And then the radius of convergence for all of these things, oh yeah, 1 over 1 minus x is this one. This is for x's absolute value less than 1. This is for all x, all x, all x. And x is between negative 1 and 1 for the rest of these three, because these all come from the geometric series. Why the difference? Well, we'll see momentarily why. Okay, so see the table on page... What page is this? right? Table 6.1. See table 6.1 in section 6.4. Now you have to know these. You will have to know these Taylor series in the table on section 6.1. All right, because we're going to use them a lot, and they're very standard, not just in this course, but in other courses as well. Ordinary differential equations and combinatorics, partial differential equations. You know, you're going to need those those Taylor and Maclaurin series. All right, let's do another example. The Maclaurin series or Taylor series for a just polynomial of degree n is again a polynomial of degree n, and the two polynomials are clearly equal. Because there's no questions of convergence, really. They just are the same. So, for example, take p of x equal to x to the third plus 6x squared minus 5x plus 2. So p prime is 3x squared plus 12x minus 5. P double prime is 6x plus 12. P triple prime is 6. And then the fourth derivative and higher is just 0. All right, fourth derivative, fifth derivative, so on and so forth. So degree n at any center. At any center. So now let's do centered at 2. 2 and centered at 1. So we need to look at not p of 0, but p of 1. P of 1 is 7 plus 2 is 9 minus 5 is 4. P1 of 1 is 10. P2 of 1 is 18. P3 of 1 is 6. P4 of 1 is 0. And P5 of 1 is 0, so on and so forth. All right, and then so we've got those derivatives. So this polynomial p of x to the third plus 6x squared minus 5x plus 2 is equal to, so it's a polynomial of degree 3, right? Because you're only going up to the third derivative. So it's 4 over 0 factorial, x minus 1 to the 0, plus 10 over 1 factorial, x minus 1, plus 18 over 2 factorial. So let me put these here. Let me put the whole thing. 4 over 0 factorial, x minus 1 to the 0, plus 10 plus 18 over 2 factorial, x minus 1 squared, plus 6 over 3 factorial x minus 1 to the third. So simplifying this, and I'm not going to multiply these out, but this just becomes 4 plus 10 x minus 1 plus 9 x minus 1 squared plus x minus 1 to the third. So this polynomial of degree 3 is equal to this polynomial of degree 3. Except this one is written in terms of x, this one is written in terms of x minus 1. These are powers of x, these are powers of x minus 1. So this is, writing a polynomial in sort of a shifted fashion. Okay, or if you're going to shift the polynomial to the left, this is the polynomial that you would get if x minus 1 was just replaced by x. Okay. So, a couple examples of Taylor series and Maclaurin series there. So now let's turn to the question of why is a Taylor polynomial equal to why is the Taylor series equal to its function, as long as you have those derivatives. Okay? Definition. Let tk, given a function f of x, which has infinitely many derivatives at some x equal to a. Okay, calculate its Taylor series sum n equals 0 to infinity f n a over n factorial x minus a to the n. Let tkx be equal to the partial sum of this thing here. So that's the partial sum of the Taylor series, and we call this the Taylor polynomial for f of x centered at x equal to a. Okay, good. So you have the Taylor series. So as usual, like what we've been doing all this whole time talking about series and such, is that we look at the partial sum. So this time you call that partial sum the Taylor polynomial. The idea here is we will show that the Taylor polynomials approximate f of x to a higher and higher degree. For example, the Taylor polynomials for sine of x are, well, there's t1 of x is just x, t3 of x is x minus x to the third over 3 factorial, t5 of x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. Remember, the even ordered terms are always 0. with the Taylor series for sine and cosine. T7 of x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, etc., etc. Now, check out this series of graphs here. So I did some graphing with Sage, made these little infographics for you. So here's sine of x, that's, obviously that's the graph of sine of x, and here's the first Taylor polynomial. It's just the tangent line, right? That's the tangent line for sine x at x equal to 0. So actually these Taylor polynomials, they generalize the notion of a tangent line and become more accurate. Here's T3. See, it's starting to approximate sine a little bit better. T5. X minus x to the third over 3 factorial plus x to the fifth over sine factorial. See? It's getting better and better as an approximation. The 7th degree Taylor polynomial, a little bit better. 9th degree Taylor polynomial. See that? 11th degree Taylor polynomial. All right, the 11th degree Taylor polynomial, it's pretty accurate for a whole oscillation of that sine function. So I mean, we have to go all the way out to degree 11 to get that, right? So this is, well, the whole oscillation is right here. One oscillation of sine. So this is minus pi to pi. Minus pi to pi. And T11 is pretty good for that whole thing. As is T9 from minus pi to pi. But it gets better. There's T13. Here's T21. So I just skipped a whole bunch and went to T21. And as you can see, I mean, you've got quite a few oscillations of that sine curve captured by T21. All right, pretty neat. So, I mean, it's like I said, right? All these functions are polynomials. Well, they're polynomials of infinite degree, but, you can approximate them pretty darn close with these polynomials, as you can see. There's other reasons why you can approximate functions with polynomials. There's this technique called polynomial interpolation. I know one of you is also in my linear algebra class, and I'm going to be going over that sometime soon in there. All right. So let me write down what this actually is. So here are graphs of sine x, sine x along with Taylor polynomials. Various Taylor polynomials. So Taylor's theorem is as follows. And we're not going to prove it, unfortunately. It's probably a little bit much to go about, about trying to prove it here, but we'll talk about it a little bit. So if, definition, given f of x and its Taylor series centered around x equal to a, f of x is equal to the kth Taylor polynomial plus the kth remainder, right? Where tk of x is the degree k Taylor polynomial, and Rkx, which is just going to be f of x minus the Taylor polynomial, is called the kth remainder. Okay, so the idea is that we want to show that the kth remainder goes to 0. If the kth remainder is really, really tiny, then the kth Taylor polynomial is going to be a really nice approximation for f of x itself, and then the entire Taylor series will have to converge to f of x. Okay, so Taylor's theorem is as follows. If the k plus first derivative is less than or equal to m, for some number m. So you take f, you take the k plus first derivative, and it's got some maximum value for all x in some interval minus r less than or equal to, well, a minus r is less than or equal to x less than or equal to a plus r. So the function, the k plus first derivative of f of x has got some maximum value in some interval. Now, that may seem kind of funny, but remember, with all these nice functions that we deal with sine x, with cosine x, with e to the x, square root of x, natural log of x, 1 over x, all these functions, okay, they often have like 1 point of discontinuity, right? Like log of x has got a discontinuity at x equal to 0, infinite discontinuity. 1 over x got an asymptote at x equal to 0. Sine x, cosine x, they're continuous all over the place. Most of the functions that we deal with are usually continuous. Pretty much always continuous, except at a point or two. Continuous functions are always bounded on a bounded interval. They have to be, because I mean, if you're on some interval from a to b and you have a continuous function, well, you can't have an asymptote because it's got to be continuous. So you can't trail it out to infinity, something like that. That's not continuous anymore. Because where's f of b? It's got to be on here somewhere. So I mean, it's just losing its continuity. So most of these functions that we deal with, they have like 1 or 2 points of discontinuity. So you just avoid them. So as long as you're avoiding the discontinuities, you're always bounded. Okay, so that's not Taylor's theorem yet, but Taylor's theorem says if the derivative, the k plus 1 derivative of f is bounded on this bounded interval, then the remainder, this remainder here, is less than or equal to m times r to the k plus 1, which is all just constant. The r is a constant, the m is a constant, over k plus 1 factorial. Or, I'm sorry, m and r are constants, k plus 1 is the variable here. Right, so, actually let me write it like this. So that's Taylor's theorem. And then so now if Rkx converges to 0, the limit as k goes to infinity, of Rkx will go equals 0 for all x in a minus r less than or equal to x less than or equal to a plus r, then f of x is equal to its Taylor series, fne over n factorial x minus a to the n for all x in this bounded interval here. Okay? In particular, now we saw in 8.1 that for any constant r, not 8.1, what was it, 5.1, in section 5.1, that for any constant little r, okay, r to the n over n factorial converges to 0. I guess we're using k here. R to the k over k factorial converges to 0 as k goes to infinity. Also, if f of x and all its derivatives are continuous, if f of x and all its derivatives are continuous on the interval a minus r less than or equal to x less than or equal to a plus r, and then they all have some maximum value, mk. If for every k it's the same value, mk takes a single value, then we must have that Rkx goes to 0 because m times r to the k over k factorial goes to 0. And this is bigger than the remainder. So, for example, right, if f of x is equal to e to the x, then, well, the nth derivative of f of x is equal to e to the x. So the interval minus r less than or equal to x less than or equal to r, f n x, is simply less than or equal to e to the r. So there's your upper bound. For all n. So e to the x has that upper bound. So by Taylor's theorem, e to the x is equal to its Taylor series on any minus r less than or equal to x less than or equal to r. That is, on all, or for all, x. So, I mean, you can say that e to the x is equal to its Taylor series on any bounded interval. But any bounded interval, you can just make it as big as you want. So, essentially, it's always equal to its Taylor series. The other example. If f of x is equal to sine x or cosine of x, then f to the n x is plus or minus sine x or plus or minus cosine x. So what's the upper bound? It's just 1 for all n. So by Taylor's theorem, cosine x is equal to its Taylor series, minus 1 to the n over 2n factorial x to the 2n, and sine x is equal to the sum n equals 0 to infinity minus 1 to the n 2n plus 1 factorial x to the 2n plus 1 for all x. Both sine x and cosine x are both equal to their Maclaurin series for any x. Well, you could center it at, instead of at x equal to 0, you can center it at x equal to pi or x equal to pi over 2 or whatever else you would like. X equal to 0 turns out to be the most convenient. But there it is. The sine and cosine are always equal to their Taylor series. Okay. Okay, so a couple of examples to end this section, a couple of applications of these. So evaluate the sums. So sum n equals 0 to infinity, 1 over n factorial. Right? What's that going to be equal to? Well, because this is equal to e, because this is the sum n equals 0 to infinity, 1 over n factorial x to the n equal to e to the x for x equal to 1. How about the alternating one? Sum n equals 0 to infinity minus 1 to the n over n factorial. Well, that's just equal to 1 over e. Right? Because this is this sum for x equal to minus 1. Right? Minus 1 to the n over n factorial. Right? How about this? So minus 1 to the n pi to the 2n plus 1 over 2n plus 1 factorial. Well, this one's got to be, right, that's the Maclaurin series for sine x. But instead of x, I plugged in pi. Well, that's sine of pi, which is 0. Right? So we've got a whole bunch of different series that we can now sum up, all related to sine x, cosine x, e to the x. Okay? Here's another neat example. So calculate limit as x goes to 0 sine x over x without L'Hospital's rule. Right? Well, this is limit as x goes to 0 sine x over x, which is equal to the limit as x goes to 0, 1 over x times the sum, n equals 0 to infinity, minus 1 to the n, over 2n plus 1 factorial, x to the 2n plus 1. Let's write out a few terms of that. So it's 1 over x times x minus x to the third over 3 factorial, x to the fifth over 5 factorial, x to the seventh over 7 factorial, so on and so forth. Put the 1 over x through here. So this is equal to the limit as x goes to 0, 1 minus x squared over 3 factorial plus x to the fifth or fourth minus x to the sixth over 7 factorial, so on and so forth. Well, as x goes to 0, right, this is a continuous function, and as x goes to 0, you just plug in 0 here, here, and here. So you just get 1. Right? So that gives you, a new way of looking at some of these limits that had 0 over 0 forms or infinity over infinity forms, and gives you a new way to look at them using these Taylor series. Okay? So that's the end of the lecture for this section.